Welcome to the first lesson of Chapter 9. Chapter 9 is about chemical quantities involved in chemical reactions. A fancy name for this is stoichiometry. The key idea behind this chapter is ratios. For example, let's look at this sandwich. In order to make this sandwich, you would need bread. I'll abbreviate that with a B. How many slices of bread are shown here? Well, 2. So we would need 2 slices of bread plus the other ingredients to make this sandwich. For example, maybe there are 6 pieces of lettuce on the sandwich, which I'll represent 6L. I also see 4 slices of cheese on there. I see about 3 tomatoes and 8 slices of meat. If I put all of those ingredients together in a combination reaction, I can make a sandwich. I could represent that sandwich by taking all of the substances and putting them together in one formula. Notice that in the sandwich, all of the pieces are connected. Therefore, I show them as one formula, all connected to one another. This is illustrating the ratios between the different substances. From this equation, I can figure out amounts. For example, I see that I always need twice as many pieces of cheese as I have pieces of bread to make this sandwich. So if I had 10 pieces of bread, I would need twice as many, that is 20 pieces of cheese. Say I had 100 times the amount of bread there. Say I had 200 pieces of bread. I would need twice as much, 400 pieces of cheese to make the sandwich. These ratios illustrate how chemicals can combine with one another in chemical equations. We'll come back to the sandwich analogy later in this chapter. For now, let's get to some of the vocabulary. The main term in this chapter is stoichiometry. Stoichiometry has 2 roots in there. You see metrie, which has to do with measuring or calculations. Stoich has to do with amounts. So, stoichiometry is defined as the process of using a balanced chemical equation. This is why we had to do the last chapter first about writing chemical equations and balancing them, in order to determine the amounts of the substances involved in a reaction. These amounts could be grams or particles or moles or volume of gases, as we will see later. In stoichiometry, you will be doing a lot of calculations. You will want to have your calculator with you as you're going through this notes packet, and also as you're doing your calculations and practice for this chapter. In part 1 of this unit, we are going to focus on mole ratios. This is the ratios that we see from a balanced chemical equation. Let's look at this example. In this case, we have a reaction given right here. This reaction is showing how nitrogen gas and hydrogen gas can react to form ammonia. NH3, ammonia, is a chemical that's used in making many fertilizers and other important industrial substances. Notice that this equation is balanced. I have 2 nitrogens on the left, and I have 2 nitrogens on the right. I can represent this with molecules as shown here. 2 nitrogens go into this reaction, and I get 2 nitrogens coming out of this reaction. This is why we balanced equations, and what we find is that those coefficients we wrote, for example, this 3 right here in front of the hydrogen, was showing me that I had 1, 2, 3 sets of hydrogen that would react together to form 2 molecules of ammonia, each of which contains 3 hydrogens. You can draw this picture on your paper. This might also help you in visualizing how to balance. Now what we find is that we can interpret this equation using moles, atoms, molecules, or grams. We're going to start by focusing on the mole. A mole, as you remember, is a way of counting. A mole represents 6.022 times 10 to the 23rd of any substance. What I want to show here is that in this picture, we had 1 molecule of nitrogen reacting with 3 molecules of hydrogen to give us 2 molecules of ammonia. What I find is that I can also express this ratio in larger amounts. For example, If I had 10 molecules of nitrogen, I would need 30 molecules of hydrogen in order to give me 20 molecules of ammonia. Notice right there, I multiplied each of the factors by 10, and the ratio stays constant between them. Likewise, I could go even bigger. I could go with thousands. I could have 1,000 molecules of nitrogen, and that would take 3,000 molecules of hydrogen. When they react, that would give me 2,000 molecules of ammonia. Now here's where we want to make the leap. Say I had 6.022 times 10 to the 23rd molecules of nitrogen. As you guys hopefully remember, that would be equal to 1 mole of ammonia, of nitrogen, excuse me. What we find is that we would need how much? Well, 3 times 6.022 times 10 to the 23rd molecules. You could type that into your calculator if you want. In other words, we would need 3 moles of hydrogen in order to react with the 1 mole of nitrogen. Guess how much we would get of the ammonia over here? You guessed it, we would get 2 moles of ammonia. That would be 2 times Avogadro's number. And that would tell us how many particles or how many molecules of ammonia we would get by reacting 1 mole of nitrogen plus 3 moles of hydrogen to get 2 moles of ammonia. What you see here are called mole ratios. So that ratio of 1 to 3, or 3 to 2, or 2 back to 1. To write a mole ratio, to do mole-to-mole conversions, we use numbers from a balanced chemical equation. Specifically, we look at the coefficients, which remember are the numbers in front of the substances in your balanced chemical equation. We look at the coefficients in the balanced chemical equation. For example, in this equation, we have no number in front of the nitrogen, which remember is like a 1. We have a 3 in front of the hydrogen and a 2 in front of the ammonia. Let's make some mole ratios. Mole ratios consist of the numbers of moles of two substances written in a ratio. For example, for every 1 mole of nitrogen, I would need 3 moles of hydrogen. Remember that MOL is the abbreviation for the mole, so it's not that I'm spelling it wrong here, that's just the abbreviation for it. I could make a couple other mole ratios here. For example, I could say 1 mole of nitrogen would react to give me 2 moles of ammonia, NH3. I can make any possible combination between chemicals in this equation. I can also put them in any possible arrangement in terms of who's on top or on bottom of this ratio. For example, I could take 2 moles of ammonia right here, change it back into 3 moles of hydrogen. We could write several more of these, but I'm going to stop here. We'll just put etc. because there are more ratios that could be made. You'll notice, though, the key thing to take away from this is that I was looking at the coefficients in this balanced equation in order to make my mole ratios. So this 3 and this 2 right here became the numbers in front of moles in this ratio or this conversion factor. Let's try using some of these conversion factors in some problems. I want to caution you that when you learned about the mole before, you might have learned that the mole always had a 1 in front of it. That was true when you were dealing with one chemical at a time. When we deal with more than one chemical at a time, you can use mole ratios, which come from coefficients in your balanced equation, to show how many of each substance you have. In this case, you will not always have 1s in front because you're looking at the ratio between substances found in the coefficients. Let's try this first practice problem. According to the following chemical equation, how many moles of ammonia is our NH3, would be produced if you used 1.2 moles of nitrogen? Nitrogen is the N2. In order to solve this problem, I'm going to start with the number I was given. So the number that I was given here was 1.2 moles of nitrogen. So I'm going to start by writing down 1.2 moles, and I'm going to include the label of N2. It's helpful to label the chemical. To do your math now, you can show this a couple ways. I usually show this with times in a line. What I'm doing here is I'm making a conversion factor. Because I started with moles of N2 right here, I'm going to put moles of N2 in the denominator of this conversion factor. The problem was asking me to find moles of ammonia, so I'm going to put moles of ammonia in the numerator, moles NH3. In order to fill in this mole ratio, where do I look? I look at the coefficients in the balanced chemical equation. So right here, the N2 had nothing in front of it. That nothing in front of it is the same as a 1. The NH3 had a coefficient of 2 in front of it, so I'm going to put a 2 in front of it. I'll make a note right here to tell you that those numbers came from the coefficients in your balanced equation. Now I'll put equals, and I'm ready to do the math. When I multiply across here, I would be taking 1.2 multiplied by 2, and then divided by the number in the denominator, which is 1. When I do this, I get an answer of 2.4. The units that I should have on my answer, well, let's see what they are. Notice I started with moles of N2, but then I had moles of N2 in the denominator. That means those units canceled out, and the units I was left with were moles of NH3, ammonia. In terms of significant figures, I see that the number I started with here had 2 significant figures, so my answer also has 2 significant figures. The numbers in your mole ratio right here, these coefficients are considered exact numbers and they do not affect your significant figures. Just to clarify, some of you might be used to showing your work in a table or a bridge where you write it with lines instead of using the multiplication sign that I used here. This does the exact same thing mathematically, and you can show your work either way. You'll notice we get the same answer for both, and again, the units canceled for both. Let's go on to practice problem 2. In practice problem 2, again, they give you a chemical equation, and then they ask you, according to that equation, how many moles of Al2O3 aluminum oxide are formed when 0.78 moles of oxygen reacts with aluminum. The number you're given here is 0.78 moles of O2. Go ahead and pause the video at this point while you try this calculation by yourself. All right, hopefully you've tried this one on your own, and let's check your answer. For the calculation, you should have started with the number you were given in the problem, which was 0.78 moles of O2, oxygen gas. I started with that number, and then I drew a times and a line, or I made a bridge, whatever you want to call it. In this bridge, I was trying to convert between oxygen, O2, which was in the denominator because that was what I started with, and the aluminum oxide, the Al2O3, which went in the numerator because that's what I was changing it into. In order to do this, notice the numbers I used here, the 2 and the 3, came from the coefficients of those two chemicals in my balanced equation. So now on my calculator, I would type 0.78 times 2 divided by 3. When I do this, I get an answer of 0.52 moles of Al2O3. For significant figures, I started with 2. Zeros in front don't count, so I end with 2 sig figs as well. We've now covered the basics of using and making mole ratios. I think you're ready to go try your homework and then try the activity that goes with this. Good luck practicing. Maybe you can find someone else to work with on the page.